Hello and welcome to this second lecture in the digital format. So today's lecture is about higher order sliding modes. So today we'll only give you the conceptual understanding of what higher order sliding modes are. We'll not explicitly discuss about any control action which is higher order sliding mode control or anything, but we have to be first clear about what we would mean by higher order sliding modes. So first we have to understand that, and after that we will be able to figure out what sort of control action will generate these higher order sliding modes. One more thing, so last presentation, you must be very clear about what is relative degree of an output, and we will also have a discussion regarding that. And as we will see in this entire presentation or this lecture, we will first understand what are the order of sliding modes and what is the difference of this with relative degree. So it might seem that these are the same things, these are talking about the same thing, but they are not. So with this warning I am starting this lecture. So constantly keep the idea of relative degree in your mind, and when I am talking about order of sliding modes, you try to figure out what is the difference. So it might so happen that in the initial slides, when I am talking about the order of sliding modes, you are unable to understand what is the difference, but when I will point that out explicitly, you will also understand. But keep that in mind, so that if you can understand it by yourself, that will be much more beneficial for you. You will have a conviction that you have understood better. So that's all. So keep that in your mind. So let us go ahead. So what is the order of sliding? So we start with the definition. So order of sliding is the derivative order of the sliding variable which contains the discontinuity. Discontinuity meaning the switching signal. So we know this, that in sliding mode control is characterized by this switching signal. So there has to be a switching signal present which switches across the sliding surface. Okay, some sin S term, some sine term has to be there. So the derivative order of the sliding variable which contains this switching term is called the order of sliding. Not only this, that definition has a second part. The system must move in the manifold where all lower derivatives of the sliding variable vanish. So of course the discontinuity has to be present in that particular derivative order, and this discontinuity must enable the system to move in a manifold where all lower derivatives of the sliding variable vanish. What do we mean by this? Let us go ahead one by one, you will have a more clear understanding. And why I have given a double star here, you see. So the system slides in the manifold. Of course that means that we must reach the said manifold in finite time. So this discontinue the switching signal, which is actually the, you think that this is a control action, but let us only suppose that this is a switching signal. So this switching signal must bring about this phenomenon. What is that phenomenon? That the system should come in the manifold which is defined by this thing, the manifold where all lower derivatives of the sliding variable vanish. This is the manifold. So, let us first check what we know, which is the first order sliding or the classical sliding mode control, how this fits into this definition. The first order sliding, how it fits into this definition of sliding mode order. Next. So, you see in the classical sliding mode control, what we have? We have S dot in something which is F1. F1 is a discontinuous right hand side. So, that is why it is an inclusion, not an equation. F1 contains the switching signal sin S. So, the whatever in classical sliding mode control we have got, we had seen that S dot equals to something something and sin S term is there. The sin S term is there in the S dot equation. So, that is what has to be understood from here or noted from here. So, the order of sliding variable in which the switching signal is present is 1 because it is S dot. So, it is in the first derivative, discontinuity is in the first derivative. That is why it is called the first order sliding or first order sliding mode. And of course, we know that what is the manifold? The manifold is defined by S equals to 0, the lower order of derivative vanishing. What is the lower order of derivative? 0, of course, because the first order sliding, the lower order from 1 is 0. So, S to the power of 0, which is S, that will be 0. So, that is the manifold. So, in the same relation, if we want to define what is the second order sliding, the second order sliding will be in the second order sliding, the discontinuity must be in the second derivative of the sliding variable. As you see, the laser pointer is here. Yeah. So, the discontinuity must be in the second derivative of the sliding variable. And where would be the sliding taking place? The sliding would take place in a manifold where the lower order derivatives vanish or the lower order derivatives are 0. What are the lower order derivatives here? For second order sliding, the lower order derivatives are S dot and S. So, both S dot and S must be 0 in this manifold. So, you see how we are defining the manifold. The manifold S dot equals to S equals to 0, which is nothing but the intersection of the manifolds S dot equals to 0 and S equals to 0. So, you imagine the state space. So, previously in classical sliding mode control, in the state space there is a surface S equals to 0 on which we come, and then we slide on S equals to 0. Now, what happens? There is another manifold S dot equals to 0, you can imagine. So, there are two manifolds S equals to 0 and S dot equals to 0, and there would be an intersection region. So, we are talking about that intersection region. That is the region where the system would come and then remain within that manifold for all future times, remain on that manifold for all future times and slide on that manifold. So, this discontinuity should be in the second derivative of the sliding variable, and it should make the system come to the second, it should make the system come to this manifold, which is the intersection of these two manifolds S dot equals to 0 and S equals to 0, and is written in this manner: S dot equals to S equals to 0. So, first order sliding and second order sliding has been defined. So, in this manner, the general rth order sliding, how will be defined? You see, the general R order sliding mode, what we must have? We must have all the where would the discontinuity be? The discontinuity would be in the rth derivative of the sliding variable. So, s to the power of r is in fr, where fr contains the discontinuity. This is some right hand side function where the discontinuity is present, and where the sliding is taking place, the sliding is taking place in the intersection of all these surfaces, where all the lower derivatives starting from s to the power of 0 to s to the power of r minus 1, not to the power of derivative r minus 1. So, all these will be 0. So, r minus 1th derivative of s and all the lower derivatives till s equals to 0, these are all 0 in this manifold. So, this is the general r order sliding mode. So, that means if one has to establish r order sliding, then he has to put the discontinuity in the rth derivative of the sliding variable, which must bring about the system to this manifold, which is the intersection of all the lower derivatives being equals to 0. So, all these, how many surfaces are there? R number of surfaces are there, and we are sliding on the intersection of this R number of surfaces. This is also something you can observe. In the first order sliding, we are sliding on a single surface. So, there is no intersection, there is no story of intersection there. In the second order sliding, we are sliding on the intersection of two surfaces. In third order sliding, it would be intersection of three surfaces. In r order sliding, it would be intersection of r surfaces, r number of surfaces, which are nothing but the lower order derivatives being equals to 0. How these surfaces are defined? These surfaces are nothing but the lower order derivatives being 0. That's all. What is the difference with relative degree? Now, if you have been able to figure out, in relative degree also we are talking about the order of derivative in which the control input appears. Here what we are talking about, the order of derivative in which the discontinuity appears, right? This is the thing what we are talking about. So, are these same? No, these are not same. These are not same because control input may not necessarily be containing the discontinuity. Yes, it is true that in sliding mode control, what we have learned so far, the control action contains the discontinuity, but that does not mean that the control action has to always contain the discontinuity. So, that is why we are going ahead, not sticking only with first order sliding. We are going for higher order slidings and trying to understand whether there is a possibility of having continuous control action also. But the definition as it stands, the definition of relative degree is a very general definition. It has nothing to do with sliding modes, sliding mode or sliding mode control. This is a very general definition for control systems. Okay, relative degree is the order of derivative of sliding variable or any output in which the control input first appears. Related to the discussion of sliding mode control, we have defined another thing, which is the order of sliding, which is the derivative order of the sliding variable which contains the discontinuity or the switching signal. Now, when the control input contains the discontinuity, then relative degree and sliding mode are same, but control input may not always contain the discontinuity. In this situation, relative degree and order of sliding mode will become different. And how this possibility can arise? we will see in an example how this possibility can arise. And first let us discuss this thing once. So again, formalizing the entire concept of relative degree. So if rho is the relative degree of the output of a system, if rho is the relative degree of the system is a general nonlinear system like this, and y is taken as the output, then what will happen? Then rhoth derivative of y would contain the control action u, and the expression will be like this. So this is these are the Lie derivatives. This we already studied in the last presentation. If u contains the discontinuity signal, and ensure, this is also important, we must not forget this, the discontinuity, we can keep any discontinuity signal, that will not work. Any discontinuity signal will not work. We have to put that discontinuity signal which ensures sliding in the manifold, this, which are the lower derivatives vanishing in that manifold. Then what will be the order of sliding? The order of sliding will be the same, rho. Then the order of sliding will also be rho. We will have rho order sliding mode for the output. So the question is still the same, when will the control u not contain the discontinuity signal? So we are this we already know. In the first order sliding mode, we know that our relative degree is 1, because in S dot u appears, and the sliding mode order is also 1 because u contains the discontinuity. So the discontinuity comes in S dot only, and we are sliding on S equals to 0. In that situation, our relative degree and sliding mode order are the same. When will u not contain the discontinuity signal? So this is the question. Let us see this situation where we have relative degree 1 and sliding mode order 2. Now how can this happen? Relative degree 1 and sliding mode order 2. What is relative degree? Relative degree 1 means S dot will contain the control input u, and this is the expression S dot equals to LAHX plus LBHXU in Lie derivative form, and LBHX is not equals to 0. For this system to have sliding mode order 2, what must happen? The discontinuity must be in the second derivative. So we must go to the second derivative. We must not stick to the first derivative. We must not remain here. We must go ahead. So intentionally we take a higher derivative. Though the control signal has already appeared in S dot dynamics, right? Then what happens? S double dot takes this form. So if you do another derivative, then using the Lie derivative formulation, this expression comes, and here you see one part of is there with u, another part is there with u dot. So if we choose u to be the discontinuity signal, then the discontinuity signal already appeared in S dot. Then we cannot talk about sliding mode order 2. Then it remains sliding mode order 1. So where must the discontinuity signal come? Where must the switching signal come? In u dot, because u dot is not present in S dot. U dot appeared in S double dot. So u dot must contain the switching signal. You see, we choose the discontinuity term in u dot, and we have to choose such a discontinuity term which will guarantee finite time reaching and sliding on S equals to S dot equals to 0. Then the sliding mode order will become 2, while the relative degree will remain as 1. So you understand by the definition how we have made an RD1 output having a sliding mode order of 2. This can be done. What advantage we are getting, you see? Then the actual control input becomes continuous. Why? Because the discontinuity is in U dot. Discontinuity is in U dot. And how do we get U from U dot? By passing through an integrator. So when the discontinuity, when the switching signal passes through an integrator, the discontinuity does not remain there. It becomes a continuous signal. So this is one advantage that we get by making the sliding mode order more than the relative degree. So if we have the sliding mode order equals to relative degree, then U will contain the discontinuity. This is true for any relative degree. Any relative degree rho, sliding mode order is also rho. That means S to the S of rho derivative of S must contain the discontinuity. Then U must contain the discontinuity. But if we make the sliding mode order more than the relative degree, then there is a possibility, or not possibility, it always will give you a control which is continuous in nature, because the discontinuity shifts to a higher derivative of the control action. It shifts to a higher derivative, in this case U dot, it shifts to U dot. Okay. There is also another advantage of taking higher relative degree as such, not just sticking to RD1 but going to RD2 or RD3. What is the advantage that we get? So you remember the chattering problem. So in the chattering problem, you see for the RD1 output with sliding mode order is also 1. Let us suppose that classical case. Then S dot will contain the discontinuity, because U has the discontinuity, S dot also contains the discontinuity. Ideally this makes S equals to 0 in finite time, but practically S dot is not equals to 0 because of the chattering. Because of the chattering, because of the finite frequency, because of the finite bandwidth of the actuators, the control cannot be implemented with infinite frequency. So there is a finite frequency of implementation of the control that gives rise to the chattering phenomenon. So S dot is never ideally, S dot should have been ideally 0, so that to maintain S equals to 0, but S dot is not 0. Practically S dot is not equals to 0 due to this chattering, and hence S equals to 0 also cannot be maintained. S also is not 0. But what about integration of S, or the matter of fact double integration of S or triple integration of S and so on? What about this? So you see, we know this, that if S is not equals to 0, suppose S is not equals to 0, S is chattering, S is chattering, that is also something we must keep in mind. Chattering means it is having value, it is moving about the 0 line, once coming to the negative side, once going to the positive side, positive negative. In this way S is chattering about the 0 line. So in this situation, integration of S, what it will be? Of course it will not become 0, but it will be closer to 0 than ST, because integration is happening. Of, there are values which are positive, there are values which are negative. So in total, you take any interval, in total the value they will compensate each other, the positive and the negative sides will cancel out each other. So we will have a value which is closer to 0. This is because ST chatters rapidly about 0, and integrating it over a time interval reduces the impact largely. If you take another integration, then that particular signal will, double integration of ST will come more close to 0. So we get lesser and lesser effect of chattering on the integrated variable if we take more and more integration. So the question is, what if the integrated variable, this integrated variable, what the integrated variable that we have taken here after taking more and more integration, what if that integrated variable is the output we are concerned with? This is exactly the case for higher relative degree outputs. If you think about it, this is exactly the case for higher relative degree output. And so with higher relative degree output, the chattering effect on the output reduces by the degree rho. For higher relative degree outputs, the chattering effect on the output reduces by the degree rho. That's why higher relative degree outputs are preferred, because the chattering effect on the sliding variable, the output or the sliding variable reduces by the order, by the degree rho. Why this happens? You see, for higher order, suppose we have a relative degree of rho, then S, rhoth derivative of S will contain the signal, contain the control input U, which contains the discontinuity. Suppose this contains, U contains the discontinuity, then rhoth derivative of S is containing the discontinuity. So practically S rho is never 0, which ideally should have been, but S rho is not 0. So in the previous situation, ideally S dot should have been 0, but due to chattering S dot was not equals to 0. Here, due to chattering, rhoth derivative of S is not 0 practically. So this will percolate to the lower derivatives of S, but the lower derivatives of S will continually be closer and closer to 0, because we are making it pass through more and more number of integrations. So the actual sliding variable or the output we are concerned with would have passed through rho number of integrations. So the chattering effect that is present on the rhoth derivative of S would have been decreased, would have reduced by the order rho, because it is passing through rho number of integrations to come to S. So we will get more closer, we will get a closer value to 0 for S than if we had chosen a sliding variable which is only relative degree 1, suppose. So you understand the comparison. So only S, if the relative degree is only 1, then the impact of chattering on S, and if the relative degree is more than 1, suppose rho, which is a larger number, suppose 2, 3, 4, something like that, the impact of chattering on S decreases significantly because it passes through a larger number of integrations. So when we see the actual sliding variable, the chattering effect is smoothened by passes through rho number of integrators. This is the benefit of using higher relative degree outputs. But the concern is that the control signal still contains the discontinuity. U contains the discontinuity. So the chattering in the control signal is still present, or the actuator is still facing the chattering problem. So how to, so the chattering effect on the actuators is still present. How to remove that chattering? Simple, we already have discussed this, by choosing a sliding mode order which is greater than the relative degree. So if you choose a sliding mode order greater than the relative degree, your discontinuity comes in U dot or higher derivatives of U dot. So the control input, when you come to the control input, it becomes continuous. Example already seen. in RD1 and SM order 2 case. So, for a relative degree rho, because relative degree of the output has also to be higher, so that the chattering effect on S is less. So, you choose a high relative degree, but then what you choose? You choose a sliding mode order which is higher than that, so that you obtain a continuous control. So, there are two things. First thing is you want to reduce the chattering effect on the sliding variable. So, you choose a relative degree which is more than 1. But now, you also want to have a control action which is not discontinuous in nature, so that the chattering effect on the actuators are also gone or reduced. So, what you do? You choose a sliding mode order which is higher than the relative degree, at least by order 1. So, at least rho plus 1, sliding mode order at least rho plus 1 to get a continuous control. So, this is what you have to do. So, this is the concept of relative degree and higher order sliding mode, and how they benefit in the sliding mode control formulation or the design of sliding mode control. So, two important things: higher relative degree of the output will cause less chattering, and sliding mode order more than the relative degree will cause the control action to become continuous. These two things. So, you see, so what we require now? We only require to know some higher relative degree dynamics which converges the sliding variable to 0 in finite time. So, this part is remaining to be known, or not just, which brings about a sliding motion actually, which converges the sliding variable to 0 in finite time. So, suppose we want to have we want to establish, or how we say this, suppose we want to make the relative degree of the sliding variable some rho, then what we must have with us? We must have with us some reaching law. So, previously we knew reaching laws: S dot equals to minus sin S, S dot equals to minus k s minus mu sin S, something like in this fashion we knew, and we were sure that they would bring the sliding variable to 0 in finite time. Similarly, in this case we must also know some reaching laws or some algorithms, some higher relative degree algorithms, S double dot equals to something which makes S come to 0 in finite time, or S triple dot equals to something which takes S equals to 0 in finite time. So, these dynamics should be with us in our repertoire, so that we can formulate a control action that generates this sort of a dynamics in the system. So, we must first know about this higher order sliding mode algorithms. Higher order sliding mode algorithms. So, these higher order, what will be the higher order sliding mode algorithm? Suppose we have a second order sliding mode algorithm, then S double dot must contain some discontinuity. S double dot must contain some discontinuity, and that particular dynamics must be such that S and S dot both becomes 0 in finite time. Of course, we must have that the lower order derivatives are 0, that is also a condition to be established. So, the discontinuity should be in S double dot, and it must that dynamics must be such that both S and S dot becomes 0 in finite time. So, such higher order sliding mode algorithms will be the point of discussion in the next session. So, we will actually discuss two higher order sliding mode algorithms, both second order. One is the twisting and another is the super twisting. These two we will have in the course. So, we will discuss them. We will see how they are behaving. We will prove the convergence of these algorithms. So, once we have this algorithm, then what we have to do? Then we can choose or deal with some higher order relative degree sliding variable or output, which reduces the chattering by the order of the relative degree rho, and then if we choose the sliding mode order r greater than rho, then it reduces chattering in the sliding variable by order r, because the discontinuity is now in s to the power of in the rth derivative, not simply in the rhoth derivative. Please note this. If the sliding mode order is chosen as r, that means the discontinuity is in the rth derivative of the sliding variable. That is how sliding mode order is defined. The discontinuity is in the rth derivative of the sliding variable. So, the chattering is reduced in the sliding variable by order r, and this also makes the control signal continuous. Because the discontinuity will not be in u, but some u dot or u double dot or somewhere like. So, now what is remaining, what is remaining to be learnt is that some higher order sliding mode algorithms. Higher order sliding mode algorithms means not first order, of course, second, third, fourth or any other higher order, and these orders of derivative must contain the discontinuity. So, if it is a second order sliding mode algorithm, then S double dot must contain the discontinuity, and we will see how many such algorithms are there, and we have to see the convergence also. So, we will only study two algorithms, twisting and super twisting, which are second order. We will not go to any other second order algorithms, we will not go to any other higher order algorithms, we will stick to this, and these two are the most important, super twisting being the more famous one, and understand their convergence. Okay. So, let me finish the code discussion here.